Greetings everyone, I'm Mehsam, a graduate student at the University of Alberta. Today I'm going to present to you prediction of in-plane shear modulus of CLT from laminate properties. This is a brief outline of my presentation. First, I'm going to discuss the background behind this research. Then I'll describe the methods and the test program. After that, I'll briefly present the results and discussions. Finally, I shall end the presentation with a proper acknowledgement. Mass timber panels, or MTP, have become very popular in the timber construction industry in recent years. Cross-laminated timber, or CLT, is a type of MTP which consists of layers of orthogonally glued timber laminates. With the advent of CLT, it has now become possible to construct tall and complex timber structures. CLT offers both high in-plane and out-of-plane load resistance in structural members. In order to get the full benefit of CLT panels under in-plane loading condition, detailed knowledge of all the relevant mechanical properties is indispensable. When a CLT panel is subjected to lateral in-plane loads, the total deformation results from the deformation due to bending and the deformation due to shear. For predicting the shear deformation, the shear modulus has to be known. Quite a few researchers have looked into determining the shear modulus of CLT. However, some of them require large-scale tests and complicated test setup. In this research, a modified and improved method for determining the shear modulus is proposed, which is also simple and convenient. The proposed modified model's final form is given by equation 1. Shear modulus G can be determined by solving equation 1 of the proposed model. E sub y in equation 1 can be determined from a uniaxial compression test conducted on a rectangle-shaped CLT section cut out at 45-degree angle to the orientation of the outer layer fibers from a larger CLT panel. The new values are the Poisson's ratio of the material of the individual laminates of each layer. T sub xm is the thickness of each longitudinal layer. T sub ym is the thickness of each transverse layer. Finally, T sub CLT is the total thickness of the CLT. Here the rest of the terms introduced in equation 1 are described. The rho average is the average density value of the laminates in kg per meter cube. Beta coefficients are adopted from Nieder-Westberg's thesis. The rest of the terms are as described here. The growth ring orientation of 45 degree is taken as the base value and assigned a value of 0. Flat stone laminates are assigned a value of -1 and quarter stone laminates are given a value of +1. The proposed model's only input property from compression test is the value of E sub y. The other input parameters of equation 1 can be determined from the material properties of CLT. Then equation 1 can be solved for the shear modulus value. Shear modulus was also determined from impact vibration test. The values from the two methods were compared to determine their consistency. This is the test setup used for the compression test. The specimen dimensions are given in millimeters. Vertical strain measurement was done on both faces of the specimen. On one side, LVDT transducer was used, and on the other side, digital imaging technique DIC was used. The strain measurement was carried out at mid-height of the sample, which was sufficiently away from the zones of stress concentration. These two figures show the compression test. To the left, we see one side face of the CLT, on which LVDT transducer was used, and to the right, we see the other face of the CLT specimen, on which DIC was used to measure the strains. The same type of CLTs used for compression tests were tested under impact vibration. For this, long CLT beams were suspended from flexible supports. An accelerometer was attached and fixed near one end of the sample. The response spectrums of the CLT due to hammer impacts along the length of the beam were recorded. The first two natural frequencies under transverse bending were identified from the response spectrum. Based on the natural frequencies, dimensions, and density of the CLT, the modulus of elasticity and the shear modulus were determined simultaneously by solving the governing differential equation according to the work of Chui. This table illustrates the CLT types used in the study. 3, 5, and 7 layer CLTs from two different manufacturers, identified as A and B, were used here. CLTs A2 to A4 have equal thickness of all the layers, whereas CLT A1 and B1 have unequal thickness of the transverse and the longitudinal layers. The specimen used for the compression test was cut out at 45-degree angle from larger CLT panels, as shown on the figure to the left. One face of the specimen was black and white speckled for the digital strain measurement, as shown on the right. All the samples were in dry condition with a moisture content around 7% at the time of testing. These column charts show the shear modulus determined from the different methods. For each type of CLT, the average shear modulus value from vibration test is given by the horizontal line. Here, the shear modulus values of A1 and A2 type CLT are shown. Here, the shear modulus values of A3 and A4 type CLT are exhibited. As can be seen on the figure to the right, the shear modulus values of A4 CLT by the vibration method could not be determined, which will be explained later. Finally, the shear modulus values of the B1 type CLT is shown here, which was made by the second manufacturer. All the results from the previous column charts are summarized here. In the left table, the mean of the shear moduli determined from the three measurement techniques have been summarized along with the variability of the data. For each set of measurement, the first column represents the mean shear modulus value and the second column represents the coefficient of variation, which is a measure of the variability of the data. In the right table, the G values from compression test is expressed as the average of the DIC and the LVDT measurements. For the A1 type CLT, the shear modulus values from DIC measurement was closer to the corresponding shear modulus values from vibration test. For the A2 type CLT, the shear modulus values from both DIC and LVDT measurement showed an overall good agreement with the shear modulus values from the vibration test. For the A3 type CLT, the shear modulus values from LVDT measurement were closer to the corresponding shear modulus values from the vibration test. Finally, the shear modulus values of B1 CLT from DIC measurement were overestimated and from LVDT measurement were underestimated compared to the shear modulus values from the vibration test. In the solution of the governing differential equation of the vibration test, the shear correction factor K is required to determine the shear modulus. The commonly used value of 5/6 for homogeneous isotropic solid beams is not applicable for laminated composite materials such as CLT. In the absence of any better estimates, Wallner-Novak's method has been used to estimate the shear correction factor. Nevertheless, the shear correction factor of CLT under in-plane loading condition is an area that has to be looked into more in future research. For A4 type CLT, the shear modulus could not be determined from vibration test, as it was not possible to determine the second natural frequency due to the presence of noise in the response function at very high frequencies. Overall, in the compression test, a 6 to 15% discrepancy between the LVDT and DIC measurement on the two faces of the CLT specimen were observed. This discrepancy between LVDT and DIC measurement might be due to the prevalence of bending in the specimen during the compressive loading. A general trend was observed that LVDT measurement yielded lower shear modulus values compared to DIC measurement. Also, for CLTs with an equal thickness of each layer, such as A2, A3, and A4, the shear modulus values increased with the increase of the number of layers of CLT. It was also found that CLT with a smaller thickness of the transverse layers than the longitudinal layers, like the A1 and B5 type CLT, yielded higher shear modulus values than the other series of samples with a higher total thickness, for example the A2 and A4 type CLT. The focus of this research was on CLT without edge gluing. The vibration test is an efficient and accurate method, but it might not always be feasible in practical settings. From the findings of this study, the shear modulus values from the vibration test and the proposed semi-empirical model were found to be comparable, thus validating the semi-empirical model proposed here. I would like to thank all the technicians of the Structural Engineering Laboratory of the University of Alberta, which made this research possible. Thank you for taking the time to listen to my presentation. The following works were referred to in the presentation. And thank you again for your time.